Let's suppose I have a clock and I want to tell you what time it is. Then I'm going to send a signal to you which says it's now 2 o'clock. But when you receive it, you don't receive it at 2 o'clock. You receive it by some time later, which has to do with the transit time. A clock on the moon, as observed from the Earth, would be running at a different frequency. That is, if you observed the clock on the moon and you observed it from the Earth, you would see the frequency is different.
Is it the same on the Mars?
No, Mars is different because Mars has a different gravitational potential. Also, there will be Doppler shifts because the distance between the Earth and Mars is changing. So the signals are very complicated because there are general relativistic effects because the gravitational potential is different, but there are also Doppler shifts because you're observing on a moving platform from a moving platform.
This week we spoke with Judah Levine, the legendary NIST physicist often called the father of internet time. For over 5 decades, he's helped define the seconds that run GPS, financial markets, and the internet itself. In this episode, we dive into what time really is, how we measure it, and how to approach the impossibly hard problem of synchronizing atomic clocks across the world. Please welcome Judah Levine.
UTC, to answer your question, UTC is a paper time scale. That is, it is a scale it does not exist as a physical clock. It's computed by the International Bureau of Weights and Measures, by the BIPM in French, based on the data from a large number of clocks in a large number of laboratories. There are about, 400 or 500 clocks in the major laboratories. Pretty much every country has a timing laboratory, and the timing laboratory maintains a number of clocks. And the BIPM computes the ensemble average, and that's UTC. Now, originally UTC. Actually, there are a number of intermediate products before you get to UTC. UTC is kind of the end product. The other products are the one that's most widely known is called International Atomic Time (TAI), and it is also computed by the BIPM based on the same data. The current version of UTC dates from 1972, when the current version. UTC existed before that, but it existed in different definitions, and the UTC timescale now is derived from International Atomic Time. That is, it's computed from international time, but it has the addition of what's called leap seconds, and the leap seconds are added periodically so that UTC does not deviate by more than 1 second from Greenwich Mean Time, which is the older astronomical time scale. Since 1972, there were 10 seconds added to UTC to maintain this link between UTC and the astronomical time scale, which is called UT1, and 27 seconds have been added since then. There is a current proposal to change the way the adjustments are made such that they will be less frequent, and that proposal is being considered at the moment, and so that the difference between UTC and UT1 will be allowed to increase perhaps to an hour, and under those circumstances there would not be an adjustment for several centuries, or not be an adjustment needed for several centuries. So that's UTC.
What was the motivation originally for creating it, and kind of what existed beforehand?
Well, the initial version of UTC had two motivations. The first one was that a timescale based on atomic clocks was much more stable than a timescale based on astronomy, which was all the previous definitions had some kind of astronomical definition, and the irregularities in the motion of in the orbit of the Earth and the motion of the Earth meant that the astronomical timescales were irregular. They had fluctuations which were hard to calculate and hard to predict, and so UTC was intended to fix that problem, namely to have a scale that was much more uniform. At the same time, it was recognized that there were a whole bunch of users of UTC who had various astronomical applications. including satellite orbits and various astronomical things, so that it was important to maintain a link between UTC time, atomic time, and astronomical time, and that was what the leap second business was supposed to do. So it was supposed to be a system that was sort of universal. That is, it provided the stability of atomic time with a link to astronomy through the leap seconds. Now the leap second business has turned out to be quite cumbersome, which is why there's the idea of changing, of decreasing the interval between leap seconds, so that the difference is allowed to increase to an hour, and that's mostly because the applications that depend on atomic time or atomic time interval have become much more important than the applications based on astronomy.
And satellites in the past, they wouldn't have an atomic clock on board, but now they do.
Well, I mean, GPS satellites have an atomic clock.
Exactly.
Okay?
So they don't
GPS
need,
satellites have an atomic
to
clock.
be using
but
the
that's
stars
not
or anything like
that's
that. Not every satellite has an
not
atomic
every
clock.
satellite has it.
Yeah.
The GPS satellites have active atomic clocks, but there are a number of satellites that are passive. That is, they are the time that they broadcast is uploaded from the ground. But the important aspect is not so much the time of the satellite as the orbit of the satellites. That is, the orbit of the satellite's position with respect to the fixed stars requires an understanding of the rotation of the Earth with respect to the fixed stars, and that's where the astronomical time becomes important, because the astronomical time is basically a shorthand for the position of the Earth with respect to to some astronomical origin, like fixed stars.
So we have heard, like, from some previous conversations that the need for time synchronization, it started from development of railways and trains.
Oh yeah, that was a rather crude need for synchronization.
Yeah.
That was more that was really the origin of the time zone system, where before the time zone system there were each local area kept its own time, which was based on astronomical observations of that at that point, and
sunrise, sunset.
Yeah,
like
sunrise, sunset, and so on, and that's very difficult when you're running a long distance railroad. You'd like to have a timetable that was more predictable, so the railroads were responsible for the time zones, or the idea of time zones, where there was a fixed time which varied by a simple number, an hour, from region to region. The other driving term was that time and frequency are really related quantities. That is, time is really a counting of frequency. And at the beginning of the 20th century, applications of frequency became very important. Mostly originally because of radio broadcasts. That is, radio stations had assigned frequencies, and there was a need for them to stay on assigned frequencies, and so applications that depended on frequency became important, and that importance has just increased. I mean, the communications, power distribution, and so on. All of these things require more and more stable either frequency or time interval, and that. Those requirements exceeded the ability of the astronomical timescales. There was just too much irregularity.
Was the original customer the military, or like the Cold War kind of like military?
No. This is way before.
Okay.
The original customers were commercial radio stations to keep them on frequency. I mean, this was
they needed like an exact frequency
precise
source.
channel. Yeah.
Well, I mean, for example, if you're a radio station, you have an assigned frequency, and you don't want to interfere with other people's stations, so you have to be on the right frequency. So there has to be a standard of frequency that all radio stations can follow, and that required a standard of frequency, and not only a standard of frequency, but a standard of way of distributing the frequency.
But I think that there's not this is probably obvious to you, but I think to listeners it wouldn't be obvious. What's the connection between frequency, like precise frequency, and precise time?
Oh, sure. They're just different aspects of the same thing. I mean, for example, if you go to the music department, they will talk about a frequency that they call A above middle C, and in the physics department, we would call it 440 cycles a second.
Oh, for sure. In terms of like the number of beats per second, et cetera, but or the number of crests and troughs. But what I mean is, if you're able to provide a very precise frequency, let's say to a radio station, have you also built a very precise clock?
Sure.
Like, are you able to measure time precisely?
It's Fourier
because-
transform. It's in the opposite way.
Well, I mean,
But how do you practically actually? You have to interfere to
you count the
precise
cycles.
frequencies, or
If you define the precise frequency, then you define a clock by counting those
Ticking,
cycles.
Yeah.
But so what's like the, let's say if you're in the 30s or in the 20s and you're selling a radio stations like a frequency source, what's that source look like? And then how do you convert that into a clock?
Okay, in the 20s and 30s, the reference frequencies were quartz oscillators.
Okay, so you have a quartz block that's oscillating under a voltage.
Right.
You apply voltage and it oscillates.
There's a physical vibration in the quartz, and the physical vibration in the quartz generates an electrical voltage. That electrical voltage is amplified, and that's the frequency. Now that frequency is compared against, in those days, the National Bureau of Standards, where there was a standard for frequency. So that frequency was compared against the standard of frequency at the National Bureau of Standards, and everybody used the National Bureau of Standards.
So there was like a quartz crystal at NIST that was like the quartz crystal.
Well, it was. In fact, it was much fancier than that. But that's the idea. There was a standard of frequency at NIST.
Okay.
It was much fancier than just that. But that's the idea. There was a standard of frequency, and that standard of frequency was compared against the local in-house frequencies at all these places, and now those in-house frequencies were used to control the stations. Now NBS, which was what at the time it was not NIST, it was NBS, compared its frequency against the frequency of other laboratories. And that was done with radio transmissions. That is, NIST would transmit its frequency on WWV, on the radio station WWV, and that would be received in other countries, and that would allow them to compare the NIST frequency with the frequency of other countries. So there was an international community of stabilizing the frequency.
So would it be better to say like maybe not the time, but like sampling, so you are in the
so I
rhythm
understand.
as precise as possible?
Yeah, so I think the question for somebody that doesn't build clocks, right? The question is, once you have this precise frequency source, and that's in the
Then you count it.
that's in the voltage domain, right?
So you count it.
How do you count it? How do you count?
Well, it depends.
Like, what is it like in the megahertz, and then how do you count that?
Well, I think the answer is the frequency that you're counting depends on what kind of device it is. For example, if it's a pendulum clock.
That's what I was thinking. Like in a pendulum, you can just connect it to an arrow and it goes like this.
Well, no, but the pendulum clock has a thing called an escapement.
It's the gear that clicks every time.
And the gear clicks every time the pendulum swings.
Exactly. Yeah.
So the counting is done mechanically.
Yep.
That is, whenever the pendulum swings, the escapement advances by one click, and those clicks are used to drive the hands. Okay, that's right. They used to drive the hands. Now,
I like your sound effects.
in a quartz oscillator, the electrical voltage is used to produce pulses, and the pulses drive a second hand. But the concept is the same. I mean, there's a stepping motor that if you look at a quartz oscillator, it goes chick, 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 chick. That is, every time the quartz oscillator counts a certain number of cycles, it sends a pulse to the seconds hand and advances it by 1 second.
So there's something that slows down, like if the quartz oscillator is in a megahertz range or something.
Well, in a wristwatch, it's not in the megahertz range; it's in the kilohertz range. But the principle is exactly the
So
same.
there's something that slows it down where there's a down conversion from kilohertz to hertz.
Counts. It's not a down conversion; it's a counting.
How do you turn 1,000 beats from the quartz crystal into a single secondhand movement?
Okay. Well, the answer is, do you know what a flip flop is?
Sure.
Okay? A flip flop is something that oscillates between two states.
Mm-hmm.
So I send in a pulse, and the system goes into one state, and I send in another pulse, and the system goes back to the other state. Then I take that, and the net effect of that is that has divided the input frequency by a factor of 2.
Mm-hmm.
Because it takes 2 pulses for the flip flop to go from the lower state to the upper state and back to the lower state again. Okay, so that every time it goes to the lower state, it happens every other pulse. I've divided the frequency by a factor of 2. Well, now I take that output and connect it to another one. And now I've divided the frequency by a factor of 4. and a factor of 8, and a factor of 16, and so on. And so the frequency keeps getting lower and lower. And if I choose the initial frequency to be exactly a power of 2, then I wind up with exactly 1 pulse per second. So in a wristwatch, in a cheap wristwatch, the frequency is exactly the input frequency is exactly a power of 2. That is, the quartz oscillator is vibrating at 32,768
It's like binary.
hertz.
It's like 2 to the power of n of.
Well,
Yeah,
it's exactly 2 to a power, and I divide it by 2, divided by 2, divided by 2, divided by 2, until I wind up with 1 pulse per second, and that drives the second hand.
Yeah, and that's amplified and actually moves that.
Yeah, I mean but you have to distinguish between engineering and fundamentals. Okay, the amplifier is engineering.
Sure.
But the divide by 2 is a fundamental. That's fundamentally what's going on.
Yep.
And now the only difference is that in the cesium standard, the frequency is much higher. In the cesium standard, the frequency is 9 gigahertz. It's in the microwave region. So I have to do many more divisions. Okay, but it's the same idea. I divide until I wind up with a frequency that I can drive a display, a counter.
I think it's also a good question, like how to precisely measure frequency.
Well, normally the way you precisely measure frequency is by measuring time interval. That is, let's suppose you have a frequency which you claim to be a megahertz, 1 million cycles per second. So you count 1 million cycles of that frequency, and you now compare it against the standard.
But you need to, so this feels like it has some kind of almost circular argument inside, because you need to have the standard in order to do this. How do you generate the standard?
The standard, I generate the standard by starting out from quantum mechanical principles.
Okay, so you don't have to look at, you're not like looking at the stars to make the standard.
No
Okay.
stars. No stars.
Okay.
I assert that if I
It's
have
based on the energy levels.
Yeah.
Okay.
If I have a cesium atom and I have an oscillator which induces a transition in the cesium atoms, then that oscillator by definition is running at a known frequency.
But there's of course like a gray zone around that, because it's, the atom could be moving and all
Doppler
these
effects
things. Yeah.
and some
Yes, of course.
broadenings.
So what you've now strayed from physics into engineering. Okay. The answer is
If you had an atom at perfect atom at absolute zero in a perfect space, you know the frequency.
That's
because
right.
You know the energy.
And now what you've discovered is that an engineered clock is much more difficult than a principal clock. Okay, engineering clock must in fact deal with all the issues that you've raised. That the atoms are moving, the atoms are jiggling, the line is not infinitely sharp, it's broad, and now you've entered quantum engineering, and that's why cesium standards cost $70,000. But you must, when you stray from the principle, you get bogged down on all these engineering details, which are perfectly valid if you were actually building the clock. But when you talk about the clock, you don't have to talk about that. You talk about quantum mechanics.
So there's this kind of like bootstrapping challenge, which is you need to have a standard in order to like improve on it or whatever. So you have to somehow start with a standard.
And the answer is, initially in 1955, the standard was astronomy. The first cesium clock, the T equals 0 cesium clock, was compared against astronomy.
Okay, so you had to refine it until at least it was as good as the...
Okay, so what I did was I ran a cesium clock for 3 years, from 1955 to 1958. And I counted the cycles, and I compared it against an astronomical time interval, and I used that to calibrate the first cesium clock.
And just to be clear about the working principle of the cesium clock is you have a cloud of cesium atoms in a vapor, and you...
In a beam.
In a beam.
Yeah.
And so, can you explain exactly like what's the working principle of the system?
Well, okay, but you have to remember that now we're entering engineering.
But we like engineering.
No, fair enough. But
Separate the different worlds.
But you have to distinguish between physics and engineering.
Well, let's say we're just looking at the physics. If you have a single cesium atom in a platonic universe, and you shine a laser on it, you promote...
No, I don't. Yeah, okay.
So this is the question.
Okay. So let's talk about the principle.
Yeah. Assume there's one atom. What do you do?
I have one atom, and it's in a known state.
Yep.
okay, that I have somehow prepared.
Let's say you're just applying a field that's
No. Remember, we're talking
doesn't
about
matter.
physics now.
Okay.
It just
fair.
converges to its
Fair
ground
enough.
state.
It's in the
Okay.
ground state, or
No,
it's
it's
a
more than
known
the ground
state?
state. It's in the ground state where the spin of the nucleus and the spin of the outermost electron are opposite.
Okay.
They're like this.
Okay.
Okay.
Why is it required?
Sorry?
Why is specifically
Because
on the
I said
nucleus
so.
and this? Okay.
Because I said so.
Okay.
Okay. The answer is I have to choose a system.
I see.
Right.
That's the
Define.
system I've chosen.
Yeah.
Okay.
Okay. I could have chosen some other system, but that's the system I've chosen. I've chosen this system.
Okay.
Okay. Where the spin of the nucleus and the spin of the outermost electron are like this.
Okay.
And now I shine a electromagnetic signal on that, and I adjust the electromagnetic signal until the state changes to this.
Okay.
Okay? All right? Now that's the physics. That's not the engineering.
Okay.
That's the physics. At that point, I announce what the frequency is.
Of the signal that you use to change the state. Okay.
That frequency is 9,192,631,770 cycles exactly, by definition. Okay? So that's an international definition that when I induce that transition, the frequency is 9,192,631,770 cycles. Okay? Now, that was decided by running a cesium clock against an astronomical observation.
Mm-hmm.
Okay? That is, I had an oscillator that was locked to the cesium transition, and I counted its cycles. And I counted its cycles for 3 years.
Mm-hmm.
Right? Well, remember, we're not talking about engineering, we're talking about concept. In concept, I counted those cycles for 3 years, and I compared it against an astronomical interval. And I asked, how many cycles fit into that astronomical interval?
Like a calendar, basically. Like
Sorry?
For exact time. How do you also fix the astronomical? Because
Just by
it may
the
also
stars.
shape.
Okay,
like,
wait.
the Earth rotation
Do you want
maybe.
to go into
Okay,
engineering?
physics. Sure.
Do you want to go into physics, or do you want to go into engineering?
Sure, let's start from physics.
Let's
first.
say there's some sort of astronomical
sort of,
source of
okay,
time.
a calendar.
A calendar.
No,
basically.
no, it's not a calendar. It's an event.
Event.
Okay. For example, I watch when a certain star passes right next to the moon.
Okay.
Okay. And I wait for 3 years until that same thing happens again.
Mm-hmm.
And I count how many cycles of the cesium beam have elapsed in that time interval.
I see.
Okay. And now that number of cycles, that was 3 years measured astronomically. And now I have 3 years measured in cycles, and I take those two, and that defines the cesium frequency.
So if in the absence of the astronomical measurement, is there another way to calibrate the clock, or you really need the astronomical measurement?
No, because because the concept of a new definition of frequency is I want to maintain continuity with the old definition of
Right,
frequency.
right.
So I want the atomic time second to look just the same as the astronomical second, or just the atomic time second, the atomic time interval to look exactly the same as the astronomical interval.
Right.
And the way I do that is by adjusting the number of cycles so that the number of cycles in a cesium second matches the number of cycles in the astronomical second. And the result of that is that nobody can see that anything has happened. When I start counting cycles in cesium, it looks just like astronomy.
I have a question on.
Wait,
okay.
before you understand, but you understand the idea.
Yeah.
Yeah. that's
Okay.
good.
All right. And now when you leave,
But that means in a way that you're not measuring time absolutely. It's more like there's some.
what do you mean? What do you mean by measuring time absolutely?
Well, so rather than absolutely would be, for example, like you have the atom in a platonic world. It's just sitting in the just one atom in the universe.
Right.
You look at the frequency, and you measure it, and you say, okay, this frequency based on the energy, which is somehow determined some other way.
I don't know it well enough.
I see. So there's no way to know the energy.
Well, it's not that I know it.
Can it be calculated from just the equations?
Sure, but I don't know the constants that go into the equation well enough.
Okay.
The way I described it is much more accurate. Okay? There's nothing wrong with your way in principle. I could use the mass of the electron and the charge of the electron and go into quantum mechanics and crank along and so on and so on.
But those constants were measured using astronomical time at some
effectively.
point. Okay,
Okay,
so that's
effectively.
Well, you can take what is
Well,
what
but
is called, I guess, a second, like from astronomy, let's say. I mean, we can come back to maybe the history of the second, and then you say, okay, second is equal to that number of ticks on the cesium.
Okay, but it's not a second; it's a day. In fact,
Sure,
you use a much longer time interval.
Yeah.
Okay, and so
But you can always convert back to seconds.
but so the way it was done was to maintain continuity with the astronomical timescale. Okay, because I wanted that when I switched to atomic time, nobody could tell the difference.
Right.
But historically speaking about the seconds, what's like the history of what it has been known to be a time equal to like a second, an hour? And
So back in antiquity, there was no such there was the what was really the fundamental time interval was the day. And depending on how you want to measure the day, for example, you could look at twilight. The day starts at twilight and runs to the next twilight. Now, that's not a well-defined quantity. What do you mean by twilight? Okay, or you could talk about a day being when the sun is exactly at the meridian. Well, that's a hard thing because the sun is a big gloppy thing and it's very bright and it's hard to measure. Okay, or you could talk about a sidereal day, when you look with a telescope and you ask when, as the Earth rotates around, when some star is exactly overhead, and I measure that the next day. Time interval was based on some repetitive astronomical observation, like the passage of the meridian transit of the sun, meridian transit of a star, the rising of the equinox. I mean, there was some astronomical effect. Right? Now, that astronomical effect was subdivided so that interval between noons or midnights or whatever you want to call it was subdivided into minutes and seconds. But that was an interpolation on the astronomical time interval.
I see. Well, where did it come to? Why is it not something like 10, like decimals, and like all the other measurements was done like in terms of length? Or like, let's say, why does it come like 12, 60?
Oh, the Babylonians like 12 and 60, but that's perfectly arbitrary. Could be anything.
I see.
I mean,
was there any like a myth or story behind why did they select that
12 and 60 are very good numbers because they have lots of factors. So that it is very natural to choose a number like 12 or 60 because it's evenly divisible by a large number of factors. But there's nothing fundamental about 12 and 60 or 24 hours. Those are, I mean, originally the idea was I was going to subdivide an astronomical time interval into subunits that were convenient, and 12 and 60 turn out to have factors to be convenient, but there's nothing fundamental about them. Maybe I don't understand the question.
Well, I understand that it's something related, like let's say, to the cycle or to the circle. Maybe then they started to like divide the circle into like quarters, like pieces.
but the 360 degrees in a circle came from the same kind of reasoning.
Yeah,
it was that those numbers have a large number of divisors that are even. Okay, and so you could make fractions of those numbers without any round-offs, without any remainders. But there's nothing fundamental about that.
Okay. Like if I would do it, I would like let's say like cutting the cake. I would do half, quarter, then it would be like a binary, like as a kind of a mantissa.
I think that's fine. But if you do it that way, you don't wind up with 60. You wind up with 64.
Yes, exactly.
So you have discovered a different system, and if you are in the computer business, you're using binary. You're probably using 64s, but that may seem more natural to you, but that didn't seem more natural to the Babylonians.
I see.
They thought of factors of 12. Well, there's 2 and 3 and 4 and 6. Okay. And the factor of 12 has many more factors than factors of 2, because a factor of 2 is only a factor of 2. I mean, that's it. Okay. Whereas 12 has 2 and 3 and 4 and 6. And 60 has, in addition to that, 5 and 10 and 15 and 20. Okay, so they're all you can make divisions very easily without dealing with fractions. So I would say that the 60 system is better than the binary system.
I mean, at some point, I guess we're heading towards like the appearance of internet.
But see, now you understand that you have now leaped forward
yeah, so
about
jumped
about
20
70 years.
yeah.
Okay, so
70
let me go. Okay, it's important to understand the principles before you talk about the engineering. Okay,
Sure, let's do it.
and so let's talk about the principles. Let's suppose I have a clock, and I want to tell you what time it is, and you are some distance away from me, so we're not okay. Then I'm going to send a signal to you which says it's now 2:00 or now sometime, and you are going to set your watch. But I'm going to encode on that signal what time it was when I sent it. Okay, I'm going to say on my watch it was 2:00. But when you receive it, you don't receive it at 2:00. You receive it by some time later, which has to do with the transit time. That is, how long did it take the signal to get from me to you? And there has to be a way of knowing what that transit time is. Okay, and because in order for me to transmit information to you, you have to know the channel delay. That is, how long did it take to get the signal to go from me to you? Okay, now that is a fundamental question. That is not we haven't entered engineering yet, right? We're still back at the fundamental question that in order for me to transmit time, I need to measure the transit delay. Okay, now, or I need to determine the transit delay some way or other, and somehow I need to communicate the transit delay to you. That is, we have to agree somehow on what the transit delay is, so that you will adjust your clock so that you take into account the fact that I said it was 2:00, but you'll add the transit delay because by the time it got to you, it was later than 2:00. And now, I'm not going to deal with the possibility that you are moving, because if you are moving, it becomes even more complicated. Because when you are moving, the transit delay is going to be changing, right? Because you are moving away from me, or you're moving towards me, and so I now have to determine the transit delay, which is dynamic, and so we're not going to talk about that. That's just too complicated. Okay, I mean, the answer is I have to do that, but I don't want to do that at the beginning. So the answer is, how do I measure the transit delay? Well, there are sort of three basic ways that I can use for measuring the transit delay. The first way of measuring transit delay is I can send a signal to you and you echo it back to me. Okay? So when you receive the signal, you echo it back to me. And I say, I measured the round trip delay, and the one-way delay was 1/2 of that. So I'm going to tell you, attention, I've measured the round trip delay, the one-way delay was 1/2 of it, and you're going to use my knowledge of the one-way delay to adjust your clock. What's the problem with that? The problem with that is the assumption that the inbound and outbound delays were the same, right? That the one-way delay is 1/2 of the round-trip value, all right? Well, maybe that's true, and maybe that's not true. In a simple medium, that probably is true, but in a complicated medium, that probably is not true, okay? So that the two-way method, the weakness of the two-way method depends on the fact that the symmetry may not be all that great.
What's a complicated medium?
Oh, sorry?
What would you define as what's a complicated medium?
A complicated medium is anything other than like a fiber is a complicated medium, okay? Or the internet is a complicated medium.
What makes a fiber complicated?
What makes a fiber complicated, the thing that in practice makes a fiber complicated is that its channel is shared with other users. That is, it is rare that I get to use the fiber all by myself.
Like a dedicated fiber, device
Okay,
to device.
if I had a dedicated fiber, then the delay would be really quite stable. But if I use a public fiber, I share that with 10 gazillion other conversations, and those conversations have to go through switching centers. That is, the connection between me to you does not use a single strand of fiber; it uses a hops, it goes from me to some station, and then from some station it goes out to another fiber, it goes to your station, and it gets rerouted at every one of these stations. Because in general, there is no direct link between me and you on a public fiber, especially unless, I mean, it might happen, but it's very rare to happen. It's much more likely that I'm going to go through a list of hops. And each one of these hops, I have to demultiplex the signal, right? I have to take my conversation out of this channel and put it into another channel. And I have to deal with the fact that all these channels are being used by many different people. So the channel can be asymmetric. The thing can be asymmetric for other reasons. It could be, for example, that there are engineering reasons why the signal outbound and the signal inbound are different. Okay, for example, let's take an example where I send the signal to you as a color of light. All right, so I'm going to send you a red signal, and I'm going to send you a red pulse, and remember you have to echo it back. Now, you can't echo back a red pulse, or at least it's not good enough for you to echo back a red pulse. Because if you echo back a red pulse, I may not be able to distinguish between your echo and the reflection of my signal from something else. Mm-hmm. Because my signal hit something along the way and a little bit bounced back. And the result of that is that you're going to send a signal back as a blue signal. So I'm going to send you a red signal, and you're going to send back a blue signal. And now I can distinguish between the signal that I send to you and the signal that comes back. Because if I see a little bit of red flash, I know that's not you, that's some reflector along the way. Okay? Whereas when I see a blue signal, I know that came from you. Well, that sounds like a classic idea. But the trouble with that is that red and blue travel at different speeds. Okay? Now, the effect in air is very small, but the effect in fiber is not small. Okay? And that's called chromatic dispersion, where the color, the speed depends on the color. So the inbound and outbound are not equal. All right? So you understand that the two-way method sounds delicious, except when you get down to the engineering, you discover that there are difficulties with the engineering. So I say, okay, I didn't want the two-way method. Okay? Or the two-way method has its problems. I'm going to use a cleverer method. What I'm going to do is I'm going to send a signal, and I'm not going to send it to you. I'm going to send it to both of you. Okay? And what I'm going to arrange is so that the delay between me and you and the delay between me and him are the same. Okay? So I send a signal at 2 o'clock. It gets to you at 2:01. It gets to him at 2:01. Okay? You compare clocks. Mm-hmm. Okay? And you decide that your clocks say the same thing so that you can compare the clocks without knowing what the delay was. Because the delay, to use the technical term, is common mode. It adds to both numbers and it's subtracted the difference.
But then we have to be the same distance from you.
Or pretty close, as close to the same distance as I can arrange it. Mm-hmm. Or the difference in distance has to be small.
Right, de minimis.
Okay, so that's called common view. Okay, so that method, for example, you hear that all the time. If you sit in the yard here, you'll hear the carillon from the Arts and Science Building. Okay, so the carillon transmits a ding at 3 o'clock, and everybody receives the ding at 3 o'clock. Mm-hmm. And it doesn't matter if the carillon is a second late, because everybody says it is now exactly the same time. So everybody synchronizes their clock to the same time, even if the carillon is not exactly at the right time, and without knowing what the transit delay is, provided the transit delay is about equal. Okay, so that's why the carillon is a carillon. Okay, it transmits time in common mode. So everybody sets their watch, and everybody sets their watch at the same time. Okay, so that's the second method. So the first method was two-way. It depended on the equality of inbound and outbound.
Peer-to-peer.
Okay. The second method, well, I would say actually this is not peer-to-peer. It's more master to follower. Okay, that is, it's really a more master to follower. The common view is really peer-to-peer, because in common view, I send a signal to you too, and I don't participate in the difference. You participate in the comparison. So common view is really closer to peer-to-peer. Okay, the two-way is really closer to leader-follower. Okay, I send you the time and you follow it. Okay, whereas in common mode, in common view, you compare clocks together, and the accuracy of the comparison does not depend so much on my accuracy because it cancels in the difference. Okay, so that's method number 2. Okay, method number 3. Method number 3 is I know that the delay between you and me varies with something else, like temperature. Okay, so for example, if I calculate the speed of sound in air, just as an example, it depends on temperature. So I measure the temperature, and I say, aha, I know the speed of sound because I can measure the temperature. So I tell you, you measure the temperature, I measure the temperature, we estimate the temperature on the path, and we calculate the speed of sound from knowing the variation with temperature. So those are 3 methods that are used for synchronizing clocks. Okay, so you understand that the whole business with synchronizing clocks depends on how you're going to determine the delay. Okay, that's the root of the problem. So the root of the problem in a clock synchronization is measuring the delay. Okay, and now when the delay varies, I have to play tricks for measuring the delay, and the internet
Go to engineering
what?
side.
Yeah, it's not even generic engineering. It's very specific engineering. I mean, the common view idea is kind of generic engineering, right? But the internet time service depends on specific engineering. Namely, I have to actually calibrate the exact link that we use. Okay, and so I perform all sorts of tricks by sending signals back and forth, and I try and estimate what the delay is, not in a generic sense, but between my channel and between the channel that links us. Okay, and to the extent that I can do that, I can transmit the time accurately. Okay, so the entire process, if you look at all the papers, the entire process is a question of how I measure the delay. All right, and it's hard. It's hard. Now, the GPS system uses a combination of all of these methods. Okay, the GPS system broadcasts the properties of the atmosphere or the properties of the ionosphere, so you can calculate the delay. It calculates it uses the common view method, so you receive the signal from one transmitter in 2 places. Okay, and it doesn't use two-way, but the two-way method exists. The two-way method is used with passive satellites, where you send a signal from here up to a satellite, and the satellite echoes it down, and then the other signal goes back up the other way, and that's a standard method, and that depends on the symmetry of the path in 2 directions. Okay, I don't know if I've answered the question or if the question has gotten lost.
Yeah, no, it's indeed.
But you understand that in the end, that's really the hard part. Okay, that in fact, when you see my clock, you really don't see my clock. You see my clock through the channel that links us, and the inadequacies of the channel are the dominant problem. If the channel were perfect, the job would be easy. And so, for example, if we have a piece of wire, if we're not too far apart and we have a piece of wire, the job is easy. Okay?
Is there a way to encode something in the signal that changes as it passes through the fiber, such that at the end, when you receive it from the signal itself, you can see how much time it's spent?
I don't know how to do that. If you got a way to do that, speak up. I don't know how to do that. I mean, you got to remember that everything I put on the signal is delayed by the path.
Yeah.
So I've got to. I don't know how to do that. Okay, I need.
Well, for the basic, I mean, this probably wouldn't work for a lot of practical reasons, but like attenuation, right? So the longer the fiber is, the more light is lost in the fiber. But then you have a lot of imprecision about how much light did you put in.
Okay, essentially, you are bringing up the amplitude stability. I mean, I mean that's just a fancy way of saying what you just said.
Yeah.
That I'm bringing up the amplitude stability and also the detection efficiency. I mean, I bring up all sorts of problems.
Right.
You know, in return for solving this problem, I now bring up another problem. So you understand that there's that you're now into engineering, okay, and you got to ask, well, which one of these problems is easier to solve?
Yeah,
and the answer is, well, I don't know. But I'm not sure I can give you a general answer for which one of these problems is going to be easy to solve, right? It depends on who are you and where are you and what are you and what do you have and there's no one perfect solution that fits all situations.
How does it work today? Like when clocks are synchronized today across the internet, how does it actually
Well,
work?
the answer is most of the clocks that synchronize along the internet use a two-way method. I send a signal out, you send it back. I divide the round trip path by 2, and I use the one-way path. And the answer is that's sort of right, but not completely right. Okay, it turns out that the asymmetry is a few percent. So, for example, if I measure the round trip time to be 100 milliseconds, a tenth of a second, then the asymmetry is going to be a few milliseconds. In other words, the difference between the inbound and outbound delays is going to be a few milliseconds, which means that the accuracy of the time transfer is going to be on the order of a few milliseconds. Well, is a few milliseconds good enough? Are you happy with a few milliseconds? And the answer is, if you're happy with a few milliseconds, peace and hallelujah, you're done. Okay? On the other hand, if you're interested in a microsecond, the internet is not good enough. And the reason is that the asymmetries are too large. And so it really depends on not only how well the thing is going to work, but how well you need it. That is,
So how does the highest performance synchronization work?
Well, the highest performance synchronization is two-way through satellites. And the reason it is the highest performance is that the paths are very symmetric. So that taking the round trip delay and dividing by 2 is a very accurate measure of what's going on.
Aren't there some the wind changes in the air
The
pressure?
answer is that those are negligible effects.
Okay, it ends up
Okay,
being
they're negligible effects. Now a dedicated wire or dedicated fiber would be very good. And the only trouble with a dedicated wire or dedicated fiber is they're very expensive, unless the distance is very short. But if between here and East Coast, the fibers are very expensive. A dedicated fiber would be very, very expensive. Too expensive. You wouldn't want to pay it. I wouldn't want to pay it, or I can't pay it. Okay.
How did you originally get into the clock business? What's the story? Like, where did you grow up? How did you get into the clock business?
I started out in atomic physics. I was trained, my graduate program was in atomic physics. And when I came to Gilla, I started working on atomic physics problems. I came to Gilla as a postdoc in 1967. And the postdocs were 2 years. That is, at that time, it was very strictly 2 years. So in 1969, when I started looking for a job, I was offered a job at NBS, what was then called NBS, and the work that I was working on at that time had to do with measuring the speed of light. It was a rather large program to measure the speed of light, and that was going to be part of the redefinition of the meter. That is, the intention was that the meter would be redefined in terms of the frequency and the speed of light, and that would redefine the meter. And now, when that program finished, it turned out that the group that was part of that was reorganized into the time and frequency division. That was a management decision to move that group into the time and frequency division. So we all got involved in the time business, we didn't start out in the time business. We kind of wound up in the time business, and when you're in the time business, you begin to think about clocks and time and frequencies and so on and so on. But almost all the people in the time business came from some other field, usually atomic physics, usually atomic structure, and they moved into clocks by some accident often.
And at the time, was it like a hot field to get into clocks? I guess there was like the space program, right? The moon landing.
This was before the space program.
Was in progress or something like that?
I don't remember that it was a particularly hot field. I don't remember. I don't. I think it was more a field that attracted precision measurement people. That is, people who are interested in in the last decimal place. And because that's what the clock that's what the clock business is. It's a last decimal place kind of position, kind of work, and you have to be into the last decimal case kind of work. And there are people who are not. There are people who would like to understand the fundamentals of the universe, but are not interested in the last decimal place of the understanding. And that's a fine thing too. I mean, that's perfectly. And so I guess that the clock business is the place where you go if you want to be interested in that kind of last decimal place sort of stuff.
And how did you get into physics originally? Like, what's the story? How did you get into science?
I guess I was always interested in electricity and radio, even as a child. Even not a child, but even when I was a kid, I made radios. I built radios. I built electrical stuff, and that kind of led naturally. I don't know if it led naturally, but that was sort of, if you wanted to get good at that, that's where you went to. Although I mean, there were other ways of doing it. You could have gone into electrical engineering or whatever, but physics was the opportunity that I had, and so that's the opportunity that I had.
Looks like radio was the inspiration toy for a lot of young kids at the time. I don't know. There was Feynman was talking about.
Well, yeah,
his biography about
that's right. But this is before all of that.
Yeah,
but that's true. But this is before all of that. I think the choices were physics or chemistry or biology, and at that time biology was not a very interesting subject. I mean, this was before DNA, before the double helix, before all that stuff, and I mean, biology really changed, but it wasn't interesting at that time, and so physics was sort of the. I guess that was. I don't remember, but it was sort of a natural thing to. It was sort of a natural thing to do. If you were interested in playing around with stuff, you naturally gravitated towards the physics department.
And this was you were originally from New York, or
oh yeah, I grew up in New York. I was in New York for through the undergraduate school. I was in New York till I was 25.
What was New York like back then?
Well, I lived in the Bronx, and the Bronx is the kind of place where tourists don't go. It's not a tourist place, and so I lived in a lower middle class neighborhood. My father was a public school teacher. He taught the sixth grade, and he taught the sixth grade in the city public schools. And in those days, and even now, sixth grade teachers were not well paid. And it's probably still true. I don't know what they get paid now. They probably get paid more now, but sixth grade teachers didn't get paid a lot. So we lived beyond the end of the subway. Okay. Which meant that it was a hassle to get anywhere because you had to take a bus to the subway. It was a real hassle.
And how robust is the system? So let's say robust, like for example, if there are like hackers who would try to break it down like try to synchronize all the clocks.
I think there are. Whenever you have a system, there are going to be hackers, and yeah, it's a problem. Okay.
How do you protect it?
The answer is there are two ways of protecting, two general styles of protecting. The first style of protecting is to have many different sources. So, for example, the NIST system has 25 servers. So in order for you to attack the NIST system, you have to attack all 25 servers.
Or like 51% of them type of thing.
Well, whatever. Like, I mean, you name a number. But the point is, attacking one server is not enough. Okay? That I can ask for time for many different servers and see if one of them is different. Okay, so that's method number one. And method number two is eternal vigilance. You watch. Okay? And you have checks, and you look, you watch. and what can I say? You watch.
How would you? What is like if you were building like a super weapon to desynchronize the clocks of? We have a theoretical nemesis, and they have synchronized clocks. How would you desynchronize their clocks with like a?
Well, first before we get involved, what accuracy do you need? Do you need milliseconds? Do you need microseconds, or do you need nanoseconds?
That's a good question. Like, what is the accuracy threshold where things start to fall apart that are important?
Well, if you're talking about public internet, then public internet is a millisecond level service. Okay, that is because there are all sorts of asymmetry problems and noise problems and so on and so on, and you're going to get millisecond level service, but not dramatically better than a millisecond. So if you need millisecond level service, you're home free. You're done. If you need better than a millisecond, it's not so easy. Now, if you have a good quality, if you have a cheap GPS receiver, you can get a microsecond, maybe a tenth of a microsecond, with a cheap GPS receiver. Something that you find in a cell phone. Mm-hmm. Okay, you probably get a microsecond without any real problem. And on the other hand, the display of a cell phone is probably not good to a microsecond. But that's not the receiver, that's the display. They simply figure you don't really care about the time to a microsecond. When you get below a microsecond, it begins to get hard. Okay, because the delay and the fluctuations of the delay and the knowledge of the delay become hard. When you get down to nanoseconds, it becomes really hard. Amateurs can't do a nanosecond. Even professionals have difficulty doing a nanosecond. The timing laboratories are at the nanosecond level, or maybe 2, maybe 3
Are there
nanoseconds.
any technologies that rely on nanosecond?
The main technology that rely on nanoseconds is the equivalent in the frequency domain. That is, it's stabilities of a part 10 to the 13, a part 10 to the 14. And though the frequencies are in the telecommunications, in 5G networks and cell phone networks and so on. And so and navigation, because the speed of light is a foot per nanosecond, roughly speaking. And that means that if you want an accuracy of a foot, you've got to have a timing accuracy of a nanosecond. So if you're, on the other hand, a cheap GPS receiver is not a 1 foot kind of instrument. Mm-hmm. It's a 50-foot kind of, maybe a 25-foot. Turn right at the next traffic light. Well, you don't have to get it down to a foot. You get it down to 20 feet, maybe. On the other hand, send a bomb through that guy's window. Well, the accuracy is probably a foot, and so you need timing accuracies on the order of a nanosecond. Mm. So navigation, serious navigation. On the other hand, and after all, an airplane is a big thing, and so you don't really care about where an airplane is to a foot. You might care about where an airplane is to 100 feet, okay, or 20 feet, or 50 feet, or some number. So it's tens of nanoseconds, and that's a GPS level. Or radar. I mean, I think ground control is probably radar, but GPS is long distance navigation is probably done with GPS.
And yeah, how would you build like a super weapon to disrupt clock synchronization?
Well, you got to remember that the clock standards are distributed. There's no single point of failure, or at least that's the intent. There's no single point of failure. And so it's designed exactly for that reason, that there's no one clock that maintains the only standard of time for the whole universe. There's a whole ensemble of clocks, and they're located at different places. And so I'm not sure a super weapon is I mean, it's a distributed problem. Now, for example, you could say, well, okay, I'm going to destroy the whole GPS system. Mm-hmm. Well, the GPS system has got 30 satellites. You have to destroy. It's a big job. It's not.
But for example, couldn't you create a false clock? Like instead of having 30 GPS satellites that you destroy, you just put up 30 more
and
that are putting out
and that's called
confusing information.
That's called spoofing. And spoofing is generating signals that are false but appear to be true. Mm-hmm. And there's a whole industry in spoofing, okay? Especially in military theaters,
What about just warming up? Let's say you know where the satellite is, and you just warm up the cesium clock in the satellite with a laser.
But the answer,
by like a,
the answer
half
is
a degree.
that's hard to do because I built a cesium clock, and I'm not going to let you get your hands on it. It's much easier to mess around with the signal on the ground.
Right.
So the spoofing guys tend to mess around with the signal on the ground, and there are jamming and spoofing attacks.
That's common.
Well, I mean, you read about it in the newspaper every day. The answer is the military is engaged in a continuous.
But if the signal is encrypted, how can you spoof it? Like, is it not encrypted?
The answer is like everything else. It's a race between the offense and the defense. Okay, and if it's encrypted, then I break the encryption, or I understand the encryption, or I decode the encryption. And now, if you think it's a perfect encryption, then you're making a mistake. It's not. Nothing is ever perfect, right?
But let's say if I shine a laser at a GPS satellite, and I find the cesium atoms,
and you burn it up.
No, you just warm it up slightly.
Well, I don't.
Just to make the time.
I think I can shield myself against that.
Just by building the satellite with enough.
Yeah, it's just a mechanical problem. You got to be cleverer than that. But that doesn't mean you send off a bomb and blow up the satellite. I mean,
that's too much. I'm just thinking of like are there any subtle ways to
well,
slightly
I think the answer is
mess with the clock?
But the real answer is that I don't build the satellites and I don't know. Okay, but the people who build satellites worry about those kind of questions.
Do like solar flares change
solar
the time
flares?
in
Solar
cesium
flares can be disruptive because they change the delay. Because the electron density in a solar flare can affect the delay, and it can affect the calculations of the delay.
So could I fly another satellite next to the GPS satellite and just release ions that change the delay next to the time, like the flight path of the photons?
I think now.
Could I just put out something that has like a high refractive index in the flight path of the photons?
Do you define that as an act of war?
I mean, for sure. I guess it would. I guess it would be. I'm just curious. Like, what are the? So the vulnerability is the assumption of the refractive index of the path to the GPS.
But let's talk about in principle. Okay, let's not talk about the details. If you damage my satellites in a way that I can detect it, I'm going to attack you.
No, but it's not. You don't touch the satellite. So there's between the satellite and the Earth, there's like a cone where the signal goes,
and somehow
right?
you do that without my detecting it.
Yeah, you would have to like heat up or change the refractive index basically somehow of the cone.
I think the answer is
very difficult.
Well, I would guess it's difficult, but you're kind of on the edge between theory and engineering.
Yeah.
Okay, and the answer is I mean, the answer is historically that's not the way the attacks are done. The attacks are done on the ground.
It's not like a laser beam also. It's like, more like a directed RF way, so it goes like everywhere. And then you're on the ground.
But historically, that's not how it's done. It's done by jamming and spoofing by rogue transmitters on the ground. That's in fact how it's done, or in balloons or in airplanes. It's not done by attacking, at least not yet, done by attacking the satellites because that's hard.
Yeah.
And not only is it hard, but I build a satellite and I think about all that stuff. And if somebody says, well, what about when they attack the satellite this way? I build it so you can't. It doesn't. I mean, and the answer is, but I don't build satellites. I don't know how they do it. Okay, but if I were building satellites, I'd worry about that. Right? And
for sure.
But
what about the fiber system? Like, can you inject signals into the fiber?
Yeah, sure.
Like,
sure. The question there is is inserting them without being detected. Okay, you got to be inside the phone company.
Okay.
Yeah. The answer is and that is the insider attack. And insider attacks are very difficult. By definition, insider attacks are difficult because an insider has access to the internals that and you got to trust. Insiders are difficult, and that's just a generic statement. I mean, the employees of NIST are potentially dangerous. Yeah, I mean,
so it's not. I feel like it's not just like a technology. It's more like a human-based
it's exactly a human factor. Yeah, of course. Employees inside the system are fundamentally a problem. Yeah,
But that must be one of the ideas behind like quantum versions of this type of information.
No, I would
right?
say that,
Where
that
you
it's
can-
much simpler than that.
Yeah.
You don't allow one person to do anything.
Right. Yeah. There's definitely there's management style ways of dealing
But the
with
answer
this,
is,
for sure.
look, all of these systems have strong points, and all of these systems have. If you're inside the system, you know where the weak points are. I mean, it's historically back as long as there have been these sorts of problems. There's a race between the offense and the defense. Do my bullets pierce the tank, or does the armor of the tank too strong? And the answer is yeah. And when the armor of the tank gets stronger, the bullets get stronger.
Maybe we could like maybe come back like in history, because you did a lot of your like studied the research during when the Cold War was ongoing.
Well, I think-
how was it like between, let's say,
Well, I think
the two sides competing
that's
with each other?
just and the answer is when you devise an attack, I devise an attack.
Was there a parallel Soviet effort to make like very accurate clocks at the time?
Oh
that
yeah,
you were
yeah.
building
No,
yours?
the Soviets have clocks that are just as good as the United States. Well, pretty much just as good. Yeah, the Soviets have primary frequency standards. Yeah, they do.
Well, at the time that you were building the Cesium standard, what was happening in the Soviet Union? Do you remember?
I don't know. I would guess
Was
that
this an area where there was open collaboration, or this was considered like military?
I don't remember, but I would guess that was not an era of open collaboration.
I think in some areas of science they were like pretty open.
But I think that was, I don't remember. I don't remember, but I don't think that was an era of open collaboration. But I really don't remember. It's 50 years ago. I don't remember. But I think it was not an era of.
Were they also using cesium, or do you remember?
Oh,
they were
everybody's
doing-
using cesium. Okay.
Why cesium?
Well, because it's the heaviest atom that's easily available. If you're going to have an atom in a beam, the cesium atoms are heavy, and so they move more slowly. And so cesium is an obvious choice. Okay, I mean, there's no any physics graduate student would tell you to build this clock with cesium. I mean,
Because
it's just,
the line widths are smaller.
well,
or-
but the line width by the uncertainty principle, the line width depends on how long you have to observe the state.
Because it's moving slower.
Because it's moving slower, you can observe the state for longer, and so there's a fundamental advantage to cesium. So every graduate student knows that. I mean, that's sort of, and that's why cesium was chosen. I mean, it's not some profound. Every graduate student would know that it's, now it turns out that there are engineering issues. That cesium is easier. It's easier to produce cesium beams. It's easier to detect cesium beams. But now you've entered engineering. But the cesium is the heaviest, easy atom to use. Okay, it's the last atom that's easy to use.
What happens after that? What goes wrong?
It become more difficult to detect, more difficult to produce, or generally speaking, the column 1 is the best. All the atoms, all the good states are in column 1, the alkali atoms. That's why rubidium and cesium, they're all cousins. They're all in column 1, and that's an engineering issue. That the atoms in column 1 are easier to produce and easier to detect, and that's just engineering. It turns out.
Is there any Moore's law in atomic clocks or clocks in general? Like, let's say, like the precision is improving over a certain time.
The precision has certainly improved, but I'm not sure that there's a Moore's law that characterizes it. I don't know. Okay, the accuracy, the performance has certainly improved by 6 or 7 orders of magnitude in 50, 60 years.
Seems like it was a big jump.
Well, the big
atomic clocks appeared.
There was a big jump from no cesium to cesium.
Yes.
Absolutely.
0 to 1.
And then there were incremental improvements, and now there's another big jump to optical clocks. But optical clocks are still laboratory devices, like Junyi's clock. It's a laboratory device. It's not. Atomic time doesn't run on Junyi's devices.
Were they deployed on satellites?
No, atomic clock.
Optical atomic clocks.
No.
Can you explain what's the like going to higher frequencies of light? Why does that improve the performance, or what's kind of the working principle there?
The answer is, when I count more cycles in the same time interval,
The uncertainty.
my
drops.
resolution is just higher.
Yeah.
Okay, so that all other things being equal, assuming everything else is equal, if I make the frequency higher, the accuracy gets better, or the stability gets better. And the problem until relatively recently was that optical frequencies were too high to count until it got to optical combs to translate them down. Okay, but until the optical combs came along, everybody understood that optical frequencies were the right thing, but they were simply unusable. You couldn't count them. The frequencies were
Because
too high.
electronics couldn't keep up.
Yeah, you can't use electronics. You had to use frequency combs.
Frequency combs, yeah.
Yeah, that's right.
What's the working principle there?
The working principle of a comb is that the optical frequency is divided down by some very large integer that you know, and so the division is that it's a very large integer that you can measure from the comb, and that's the essence of the trick.
And then you can put it into normal electronics or high-speed electronics.
Then I can put it, once I get it down into the gigahertz region, I can use normal electronics.
So that's the frequency comb. They kind of open the path towards optical atomic clocks to synchronize the atomic transitions with the laser.
Okay. Before that, everybody understood that an optical clock was the right thing to do, but there was no way of counting the frequency until the combs came along that allowed the translation of the optical frequency down into a microwave region where it could be counted.
Yeah, I think it would be great if you could also explain that how the atomic clocks work in the sense that, like, you have an atom and then you have like electromagnetic field that you are trying to measure the frequency.
But so let's talk about cesium beams, because
yeah, sure.
Okay, so the first step in this, remember, you got to, the first step in the business is to make a beam, right? You got well. It turns out that making a beam of cesium is very easy. You have a little kettle, and it's called an oven, but it's basically just a small block with a very small hole in the front.
Evaporate it. And
you evaporate the cesium, and cesium is very easy to evaporate because you have to get it to like 50 C, and it evaporates because cesium.
In a vacuum,
it's almost cesium is a solid, but it almost melts in your hand. Okay, it melts at like 27 C. So you heat it just gently, and the cesium beams stream out of the little hole in the front of the thing. So now you have the beam of cesium. So that makes the beam of cesium. So that's the beginning, and so the oven is just a block with a heater and a cesium thing and a small hole on the side. But now you have to set it up so that you get the atoms in the bottom state, right? You have to decide. Remember, because you got to arrange it that the atom has to be in the bottom state, because that's how the clock's going to work. All right. Well, the way you do that is that it turns out that the bottom state has a unique magnetic property. Okay, and so you run the beam through a magnetic field.
And you filter it.
Okay, and it turns out that if you make the magnetic field just right, the atoms in the state that you want get through, and the other atoms are deflected out. So all the atoms go into the magnetic field, but only the good guys come out. Okay, and the good guys are the ones in the lower state.
What's the condition for this? Is the magnetic dipole?
Magnetic moment.
Magnetic moment, yeah.
Yeah.
How was this found? Like, how did you guys find this filter? Like,
it was
already known, or you had to find it to.
It was known. I mean, there was a lot of work on atomic beams for years and years. But there's some theory, and then there were some measurements. But the measurements of atomic structure date back to before atomic clocks.
But is this something that, like, when you were building the clock, you had to basically figure out, like, okay, how are we going to purify the atoms? Or?
That idea had been developed earlier. Okay. The magnetic selection was known earlier. It was back in the Stern-Gerlach experiment. The Stern-Gerlach experiment, back 30 years before, demonstrated that fact that you could separate the beam based on the magnetic moment. Okay, using magnetic separation. Okay, so back in the Stern-Gerlach experiment, back in 1920, it was known that you could separate a beam based on the magnetic moment, so the states were physically separated. That is, one state was deflected relative to the other state. So you just put a stop at the output so that only the good guys get through. Okay, so there's a mechanical, knife edge or stop. So the only good guys get through. So now what comes out of the beam is only the atoms in the lower state. Right? That's all you get. Now I irradiate that beam with my oscillator, with my microwave oscillator, and I adjust the microwave oscillator until the atoms change state. Well, how do I know that they change state? Answer, I do the same magnetic trick again. Okay? So I have another magnetic thing, except now only the atoms in the upper state pass through. So I start out with atoms in both states. They go through the first magnetic selector, and now only the atoms in the lower state get through. Now I shine microwave radiation on it, and when the microwave radiation is right, the atoms flip it to the upper state. So now the atoms in the upper state, and now I have another magnetic selector, and now it's adjusted so only the upper state passes through.
And then you measure a RF frequency when most of them will switch.
How do you detect cesium atoms? What's the detector?
Okay, it turns out that that's a magical fact of cesium atoms.
Okay.
And that's one of the reasons the alkali atoms are used in general. If a cesium atom hits a hot platinum wire, okay, the cesium atom is ionized, and it comes off. It goes in as an atom and comes off as an ion, and essentially the electron is stripped off. And now I have a charge, and now I simply detect the charge. I simply count the charge.
On the platinum wire, or
no?
the atom itself?
I have another
cathode or something like
cathode off to the side, and I simply attract the guys and I count them. And that hot wire detector is magic of the alkalis. It only works. Essentially, it only works for the. That's one of the reasons the cesium was chosen.
Wow, that's a really cool detail.
Okay, so now in subsequent years, there are fancier methods. There are fancy.
Is the wire the anode, and so then it ends up being like a balanced system? Or
there's a wire, and the cesium atoms come in, and when the cesium atom hits the wire, they come out as ions. And now over here, I attract them with a negative thing, and I simply count the number of ions that reach my detector.
But the electrons, do they build up on the platinum wire?
Well, they just go. I mean, they don't build up. They just they get siphoned off the ground.
Okay, interesting. How was that discovered?
I don't know, but it was a well-known thing long before cesium clocks. It was a well-known idea. It was called, there are a number of different effects that are the same effect. There are some atoms which if they're in the excited state, when they hit the wire, they send off an electron. I mean, so there are a number of different configurations in the hot wire detector. What you get off is an ion, but sometimes what you get off is the electron. So sometimes you're counting electrons, and sometimes you're counting ions. But the concept is the same. You change the neutral into a charge.
Was there any limitation to how many charges you could detect versus how many atoms you could produce or anything like that? Like, what was the?
I mean, the detection efficiency was tiny. Okay, so that the beam is, I don't know, thousands of atoms or maybe a million atoms. It's tiny. Okay.
So you need to amplify the signals what you're measuring.
Yeah, but see, now you're just dealing with electronics. Okay, that's the physics. The physics part of it is over. Now it's just electronics. Now you just have amplifiers and detectors and meters. That's all. I mean,
I guess you don't even need an absolute number. You just need a threshold at which you can say this is the best frequency. Like essentially, if I go higher than this frequency, it gets worse.
That's right.
If I go lower, it gets better.
Well, in fact, what you do is you jump back and forth across. Right. Yeah, yes, that's right. That's exactly how you do it. Okay, you jump back and forth across the maximum, and you jump back and forth, and that's exactly how you do it. You find that peak.
But the width of the peak, I guess, does depend on, like, the uncertainty of the peak depends on the detector.
Yeah, but now again, that's right. So now the width of the peak depends on how long you get to observe the atoms.
Right.
So now you see you can't completely divorce the engineering, but the answer is yeah. Okay, that's right. You want to make the peak as narrow as you can, and so that means you need as long a tube as you can get. Okay, so the natural thing is to make the tube absolutely as long as you possibly can. Right? Well, in commercial cesium devices, they have to mount on racks, so the length of the tube is 19 inches.
So because maybe this is me being slow, but if the tube is longer, the atom travels through the tube a longer time, so it's irradiated for a longer time. Why does that increase the accuracy?
Because the uncertainty principle says that when I observe a thing for more time, the uncertainty in the frequency is reduced.
But are you observing it for a longer time?
Sure.
Because the observation time is really when it hits the detector.
No. The observation time is in the irradiation time.
Why is that?
Because once the irradiation time is over, the rest of it is just detection. The state has already been transmitted. The state change is already done.
So you're saying
High
that
chance
the
to
longer
absorb.
it passes through the tube, the higher the chance it has to absorb the frequency.
Yeah.
Yeah, okay. So there's also a question of like, what are the chances of it actually absorbing the...
Well, the answer is if it doesn't absorb, it doesn't. I mean, you have to, but now you're into efficiency.
Yeah.
Okay, that's simply a matter of what's the efficiency of the absorption. Okay. Right? Do I manage to get all the atoms or only 10% of the atom? That's
Well, I guess what it is the atom is observing the frequency as it's passing through in a way. And the frequency also has some instability. So the longer it passes through the frequency, the more it's like averaging over the behavior of the frequency
what you're saying is absolutely right. But you've strayed into engineering again.
Okay.
You've strayed into the question of, well, now how do I actually build this? Okay. And so you want to make the tube long. You want to make the frequency stable. I mean, you have to do all those things. That's all. But that's absolutely true.
No, I'm just trying to understand where this like accuracy increase comes from by making the tube longer.
Oh no! It's not. The accuracy does not increase. Okay. Well, in some sense, it does increase because the line becomes narrower and the top of the line becomes sharper.
Exactly. Yeah.
Okay. But the accuracy has other terms. Okay. The accuracy has other terms, and because we haven't talked about the other terms yet. Okay, but let's just stay with this. You understand this? I want to make the tube as long as I can, and so the natural length of the tube is a cesium fountain. I don't make the tube horizontal. I make the tube vertical. Right, and I shoot the atoms not horizontally. I shoot the atoms vertically, and I shoot them so slowly that they go up and they come down and they fall down again. Right? And now the interaction region is the interaction time is very long. All right. And so the result of that is that the potential accuracy is much better. And so all of the ultimate standards are not the devices that you see out there. They're fountains. They're not horizontal. They're vertical.
And what's the largest
It's about
fountain clock?
2 meters.
So they didn't try to make it
Well,
taller and taller?
back a long time ago, they tried to make it. The engineering just becomes impossible.
I see.
Okay, it just becomes extremely difficult. I mean, there was a time when they wanted to make a standard that was like 2 floors, 16 feet high, but the engineering just becomes impossible. Okay.
What's the challenge?
I think the challenge is getting the beam to come down again.
Oh, I see. It spreads a lot, and then
I don't know. I've never built a clock, but
Absorbs through the walls and
but you see, there are all sorts of problems waiting to be talked about that we haven't talked about yet. Okay, for example, one of the problems is that the cesium atom is not completely isolated from the rest of the world. It collides with other cesium atoms. Well, when it collides with other cesium atoms, that's very bad because that changes the energy levels.
Molecules? Do you have to form molecules? Or?
Well, it collides with air, but it collides with... I mean, remember, this is a beam.
Yeah.
So there's a whole bunch of cesium atoms going up. Well, they collide with each other, okay? So that's an effect, okay? There are effects where you have stray magnetic fields or stray electric fields. So all these things affect the transition frequency. And they affect the transition frequency in a systematic way. That is, the transition frequency, when you have a stray electric field, is not the transition frequency that you think you have.
How do you shield from stray fields?
Well, the answer is you have shields. Okay, you have magnetic shields, you have electric shields. I mean, you have shields and shields and shields.
Do you like coat the glass cell with some
Oh no, magnetic shields, mu metal. They're
like electric fields?
electric fields are relatively easy. You just have a closed, very good conductor, like a copper sheet, or a okay. But any good conductor is okay.
But then don't you block it? Like a ref would be reflecting back.
Well, the answer is you have to have little holes. Okay, that's right. I mean, see, but the answer is you make a shield, but now you have to have a little hole to see what's going on. Well, that's a problem.
I see.
And what was the biggest of all the noise sources and like these kinds of practical issues? Which ones were the most like challenging or like had interesting solutions?
Well, the collisions between atoms is a serious issue. The collisions with the walls, to the extent that there are collisions with the walls, is a serious issue. Straight magnetic fields.
But how can you control for collisions between atoms? I mean,
by using a lower density.
Mm-hmm. So tuning it down to the point where it's almost.
That's right. But the problem with using a lower density is you have a lower signal.
Shot noise. Right?
Okay, what?
Shot noise, like fewer.
Well,
atoms
but that's right. But if you have shot noise, but if you have a lower density, you have a little fewer collisions.
Yeah.
So now the question is which
broadening, like.
That's right. And but the problem with with lower density is you have a lower signal, so you begin to get electronic noise, or electronic noise becomes a more serious issue.
And so why did you run the clock for 3 years? Was that an arbitrary number? Is there like a fundamental reason?
No, because the astronomical event is hard to detect. Because you've got the day-to-day variation of the astronomical event. Remember, you're seeing the transit time of a star through the jittering atmosphere. So there's atmospheric scintillation, and it becomes hard to detect. You've got to average over a very long period of time.
And how did you know, like, when you thought the clock was good enough? Like, what was your, how did you decide, okay, now we're going to do the 3-year measurement?
I don't know. I think you ran the experiment as long as you could stand it. I don't mean
why did you stop at 3 years? I mean, why did you start? Like, let's say what year? I don't know what year you started the 3-year experiment.
1955.
Okay, so in 1955, how did you know that the clock was good enough to start like the long experiment without making any
I didn't know how to make
changes?
it any better.
How did you know that it was? How were you like measuring its goodness? Like, what was the?
I built two of them and compared them.
Okay, interesting.
Okay, I built two of them and compared them.
Well,
and so you would tweak one and see if it improved the repeatability or something like that.
And I sat down and I thought, what are the problems? I mean, you understand, it wasn't me, okay? It was Perry, okay, and so on, and you sit down and you think about it. You make it as clever as you can, and then you build two of them.
Mm-hmm. And so you'd make a tweak in one, and that'd be version 1.10 or whatever, 1.11.
Yeah, well, and you make it as best as you can, and then you say, this is best as I know how to make it. It's time to start the experiment.
And the figure of merit was like the stability of the frequency that you were. Like day to day, what's the stability?
Yeah, it's like a part out of 9.
Okay.
It was by current standards, it was very crude.
Mm-hmm.
It was like a part out of 9, part out of 10. It was several orders of magnitude poorer than the ones today. There's been a lot of engineering developments to make things better.
So at that time, how long did it, or like the whole team to build the Cesium clock? Like how long does it take, like, to build a clock?
Yeah, how many people were building it, and how long did it take?
There were 2 of them, and they were in the UK.
That was the first one, right?
Yeah,
I guess maybe here you were involved in.
Oh no! It was way before me.
Yeah.
Oh no! It was way before me.
No, the one you built. Did you build the atomic clocks?
By the time I built the clocks, the engineering was well understood. I'm not sure I understand.
This question is just when you were building the clock that ended up, creating UTC. How long? Did it take to build that?
The clocks that create UTC are commercial devices. I didn't build.
So maybe tell us exactly what you were doing in the 50s. Like, what did it look like?
No, not in the 50s. It was in 70s.
It was the 60s. It was 60s and 70s.
60s and 70s.
The answer is understanding the statistics.
Okay.
That is because the clocks are imperfect. and you have to model them. If you have an ensemble of clocks, they all disagree with what the time is. And the question is, what's the best estimate you have of what the time is, given that you have a bunch of clocks that don't tell you the same answer?
So, like especially with recent advances in like machine learning and AI, kind of data science approaches, do you see the way to kind of improve the collecting the data on the clocks to improve the performance?
AI doesn't.
I would say maybe data science. So you collect a lot of data, but then you will try to feed to optimize the performance of the clock.
Yeah, I think that's right. That's the right idea. Okay. But
since each of the clock, it has like its own personality, its own.
you have,
Oh, here we go.
okay. The answer is you have frequency stability of the clocks and
Yeah.
time stability of clocks, and you have different clocks, and you try and model when you have an ensemble of clocks, you try and model the behavior. I mean that's just called the Allen variance. It's just a way of doing it, but conceptually you have an ensemble of clocks that don't agree with each other. And you have to try and estimate what's the best information that I have from the ensemble, given that the ensemble does not agree, that the individual members of the ensemble do not agree with each other. So it's basically a statistics problem, but it's a statistics problem of a style that was not understood beforehand. That is, it was not. That was one of the primary developments of the era, was understanding the statistics of atomic clocks and how you take an ensemble average and get the best you can out of the ensemble clocks.
What were you doing besides literally, if you have 10 clocks, just averaging them? Like, what's the
Oh, no,
trick?
averaging is not good enough. And the reason averaging is not good enough is that the clocks don't have noise, they have systematic variations. That is, there is clock number one, in which the manufacturing tolerances are that its stray magnetic field is a little larger. And so averaging that clock does not help you. You get the wrong answer time after time after time.
Adding inaccuracy.
Okay, it's an accuracy problem.
Yeah.
So you have to estimate the systematic errors as well as the random errors. Okay, and the systematic errors in the end eat your lunch.
But how do you know the systematic errors? Let's say you have 10 clocks. You don't know which one is right.
The answer is I learn by sending the data to the BIPM and comparing it with other laboratories. And we have a community understanding of the systematic errors. So the BIPM provides a community understanding.
And so basically, in order to set the time, let's say you have 10 clocks and you have a formula, like each clock contributes its own little bit to the formula. And you say, okay, given that this is the time on all these 10 clocks and here are my fudge factors for each clock, this is what we think the time is.
Right.
Okay.
And now I take that time and I send it to the BIPM. And the BIPM says you're 2 nanoseconds fast with respect to everybody else. Or you're 3 nanoseconds slow with respect to everybody else. Or in fact, what they send me is a table that every 5 days they tell me where I am with respect to everybody else. Okay. And they say, 2 nanoseconds. On last week, you were 2 nanoseconds fast. This week, you're 3 nanoseconds fast.
So there's partially an assumption of this kind of, you're essentially manufacturing reality by saying like, okay, we're going to have multiple places where everybody tries to come up with, reality. And then we're going to compare it with each other and try to guess at like, we don't know the hard truth, but given that everybody's sources of error should be different.
What do you mean by hard truth?
Like, because there's no clock, like there's no like actual, it's all clocks with errors, right? You're basically saying like, we think that different labs have different sources of errors. So if like, let's say 3 out of 4 labs are slow versus the fast one is probably has an error.
Okay, but
should be.
But what you have come to the idea is that time is a human construction.
That seems to be the case based on this discussion.
Time is a human construction. Yeah. When I say it's 4 o'clock or 20 after 4 or whatever the time is, it's a human construction. And we all agree that when you say you're going to be here at 2:00, we all agree what 2:00 means.
We synchronize.
We synchronize
You're at
our
the right
clocks,
place at the right time.
And it doesn't matter what we call it. All right.
Okay.
But we all agree that you're going to show up here at 2:00, and we all understand what 2:00 means.
Okay, but there is a platonic time. We just can't measure it, or no?
I don't know what that means even.
Like a theoretical time, like kind of like math. You know, like 2 + 2 is 4, even if nothing else exists.
But time does not have that quality. Time is a human construction.
I think like it's all in terms of synchronization. Like object A gets into point B.
But the only reason, the most important aspect of time is that it's a way of so that everything doesn't happen at once.
But do you think math is a human construction? Math, like just summation or something like that. Does that exist?
But math and time are not the same thing.
No, I know, I agree. I'm just saying, do you just to set a baseline? Like, do you think math exists outside of humans inventing it?
I think algebra exists outside of human construction, but time does not.
Okay.
Time is a human construction. It is simply that it is a way of organizing society, such that we look at the clock and we all agree to do the same thing at the same time, but we instead of calling it 2:00, we could have called it 3:00 or 8:00 or 12:00 or whatever it is.
So let's say you have all these physical things happening, atoms moving around, chemical reactions, whatever, the entire universe. Everything happens with respect to time, whatever that is.
But you have to be careful to distinguish between time and time interval.
Okay.
Time interval is different.
Time interval you think is real?
Time interval is basically a number of cycles of cesium and is real.
Mm-hmm.
Yeah. Time interval is real.
Do you think that if there was like a drift in the universe, would we see it in the
Maybe
work
not.
that NIST
Maybe,
is doing?
well, there are people who are looking for that. The answer is, okay, one way of looking for it is, let me look at the light from a very distant star.
Mm-hmm.
Okay? And the light from a very distant star left the star a long time ago. All right? Do I see something funny about the light from a distant star? The answer is, I don't know, not yet. But if I see something funny from a light from a distant star, I've addressed your question.
But in clock systems, is there no chance, because they're like kind of like circular reasoning?
Well, I think the answer is it's a question of magnitude.
Because they're operating for such a short time.
Well, I mean, the stiffest test that you've talked about are to look at the light from a distant star.
Because it's just existed for a very long time.
Because it left the star a very, very long time ago.
Right.
I mean, those are the stiffest tests.
It's like a latency, delay.
Was that?
I mean, the for the light, like from the star.
Yeah.
Yeah. Well, it left the delay. It left the star billions of years ago.
Is there nothing else like that? Like if you just pick up an object, right? Does it contain nothing that like records time?
No, you got to always distinguish between time and time interval.
Right.
Okay. So the answer is,
well, like the passage of time. Let's say uranium decays over time, right? Stuff like that.
All atoms have implicit time interval, implicit frequencies.
Right.
But that's not time. That's time interval.
It's like cycles. Like
it's a number of cycles.
So let's say if the frequency of the cesium shift was subtly changing over, like, as the universe gets older, would you guys detect that, or would that be kind of cancel out in all of your
I think the answer
equations?
Is maybe and maybe not, because in order for me to detect that, I need to have something to back up against that does not change.
Right.
So now you have to identify it's changing in the cesium frequency, but somehow everything else isn't changing. Or
something else has to
there's something
change.
else not changing.
Right.
And I don't know. Okay. I mean, for example, the question is, are there atomic properties that are changing in a way to change the cesium? Because the cesium frequency is derived from atomic properties.
Right.
Well, maybe one of the atomic properties is changing. Maybe the mass of the atom is changing, or maybe the charge, or whatever. And there are people looking at those kind of questions. Okay? But those are atomic physics questions. Those are not really clock questions.
But I guess you could use a clock to probe some of that.
You can
because
use
it's the most precise.
That's right. And there are a lot of experiments which look for those kind of experiments. And the answer is, nah, there isn't a systematic. There are tantalizing evidence that maybe. Let me say it that way.
Okay. What's an example of that?
There's a thing called the fine structure constant, which may be changing. The fine structure constant is a combination of atomic properties, which turns out to be a real number, 1 over 137. It just turns out to be it turns out to be a well-known fraction, and maybe it's changing, maybe not. I mean, I don't know. The data are very poor. The data are very noisy.
It's interesting that alpha it was like defined in a very kind of dirty experiment, like that for
Well, I think
experiments
the variation of the fine structure constant is an active experiment. I mean,
it's the quantum Hall effect.
I mean, the idea is
But
to find something which varies with the fine structure constant differently from the way something else varies with the fine structure constant, and then see if those two measures of the fine structure constant diverge from each other. And I'm not an expert on fine structure constants, but I don't think so. I don't think the data are definitive. The data are suggestive.
Speaking of time, like time intervals, so I see now it's more like in, let's say in quantum mechanics, or like in atoms, it's more like cycles, like how many transitions are, or how often do they happen. But then if we look at the like general theory of relativity, those like the space-time continuums.
Sure.
How do we bring this into?
Well, I think general relativity has an impact that what you observe a clock depends on where you are.
Right.
And where what your gravitational potential is, and are you moving with respect to the clock, or is the clock moving with respect to you, or is the clock at a different gravitational potential? And so general relativity has a lot to say about that. But general relativity doesn't affect what happens if I have a clock right here in my hand. You know, that's my local time. That's the proper time of the clock. And the proper time of the clock, I'm moving with the clock. Every test that I have doesn't detect that effect.
Could clock be one of these teaching points between?
Say it again.
Could like time definition or clocking could be like the defining, like this teaching point between like general relativity and the quantum mechanics, because it seems like what you define the time, it's more on the transition of the atoms.
I don't know. I don't know. I don't know the answer to that. I don't think so, but I don't know. Okay. The question is whether relativity is applied to quantum mechanics, and I don't think so. I don't know. That's something I really don't know about.
Also, for let's say young scientists coming to the field of let's say clocks or precision measurements. So there have been tremendous progress. Let's say building the atomic clocks. Now we can use like this. Let's say optical atomic clocks, like going to precision like 10 to minus 19. What is left? Like what are the next biggest challenges you see, or like the problems unsolved?
Well, I think there's you got to remember that that having a clock in your laboratory is very exciting, but using the clock presents all sorts of challenges, and that has to do with characterizing channel delays and 5G or 6G or whatever, or synchronizing widely spaced clocks or widely spaced generators. And those are not trivial issues. It's difficult. It's difficult to exploit the full capability of atomic clocks with remote synchronization. It's possible, but it's very difficult. That is, it's very hard. If you and I are separated by a continent or some fraction of a continent, it's very hard for me to tell you the time with the accuracy that I know it locally. That is, I know the time locally, but it's very difficult for me to tell you the time in New York City with the same accuracy that I know it, because the transmission delay and the knowledge of the transmission delay and the characteristics of the channel and all of that stuff are very important. And in fact, they in most situations they dominate the problem. So that having a clock here. Unless I have another clock in the same room, I can't necessarily exploit the advantage. For example, it's very difficult if Junyi's clock would have worked perfectly, it would be very difficult to exploit it. Because it would be very difficult to transmit the time with the accuracy that June knows it.
I see. So that's the kind of the communication channel problem.
It's a channel problem. It's a receiving problem. It's a signal to noise problem. There are all sorts of problems. But the channel delay is one of them. Yeah, channel delay is an important problem.
Are there any ideas on the horizon how to improve the channel problems?
Well, there are dedicated fiber circuits. There are, but the main problem with the channel problem is that is that good channels are expensive, and they tend to be point to point. That is, it would be possible for you and I to transmit time to each other on a dedicated channel. It would be expensive, but we might be able to do it technically. But it's a point-to-point transmission. Namely, if I now wanted to transmit time to your buddy, I now got to repeat the whole thing all over again. Okay, that is, it's not so useful. So we've made point measurements, but we haven't made a global measurement. But the transmission problem is a very serious problem. It's even without optical clocks, it's very difficult to transmit the time to a remote user as well as it's known locally. It's possible, but it's very difficult.
Let me see. So that clocks maybe with high accuracy they could be used for maybe as some sort of like sensors.
Maybe,
but maybe not as like a distributive network.
Well, I think that the development of clocks has outstripped the development of transmission medium. I think that's a better way to say.
So it's kind of lagging behind.
Yeah, it's lagging behind, so an important development is to look not at the improvement of clocks, but at the improvement of transmissions. That is a very important aspect.
Is it more of like an engineering type of problem, like materials?
Yeah, it's
cheaper fibers.
Yeah. Well, okay, but it's also
channel.
It's also a matter of principle, in the sense that engineering is important, but let's talk about the physics. I mean, how am I going to measure the delay?
Yeah.
And what mechanism am I going to use for measuring the delay, and how accurately can I do it? And so now, after I decide on that question, I have to decide on the engineering questions. Okay, how to actually build it, that's another issue. Okay, but I've given you the method. I mean, the two-way method, the common view method. Those are the ways. And now maybe there's a cleverer way that we haven't thought of yet, but those are the ways.
Are there any driving use cases, like driving this technology, or we're like more or less happy with?
Oh no. There's always a driving use case. Okay, there are always people who want more.
Yeah.
Okay. There's 5G, there's 6G. There's always people who want more.
How much do we need for 6G? What's the requirements?
I think 6G. I don't know. I'm not a telecom engineer, but I think 6G could probably be accommodated with the existing clocks, but I'm not sure about the transmission medium. I'm not sure about that. I'm not sure that's an authoritative answer. I don't know.
Let me see. For GPS, I guess GPS is
GPS uses commercial clocks, uses rubidiums and cesiums.
Let me see.
Now, the next generation of the GPS-like satellites may use hydrogen masers, or maybe optical clocks if they were reliable. I mean, the trouble with optical clocks is at the moment they're not reliable enough. You can't put them up in a satellite because they don't have a long enough lifetime.
What's the advantage of hydrogen masers compared to cesium?
They have very good short-term stability. The short-term stability is the best of all of the commercial devices.
I see. And the global navigation system, I guess, it's more like high precision. Is it? I assume like more like for military purposes. I don't think for civilian.
Well, I think there's I mean, certainly there are military applications, but the GPS system is used for synchronizing telecom.
I see.
Cell sites and so on. You know, it has commercial applications. I mean, it's the backbone of the cell system.
What about the Starlink? Do they need better
I
clocks?
don't. Okay, I don't know. I don't know. I don't know. If Star, I don't know if the, I don't know if are the satellites in Starlink active or passive.
Active.
They're
okay,
active.
Here
Okay.
we go.
So they're active. Okay. But the question is what kind of clocks do they have on the board? I mean, I don't know what they have. I don't know. I mean, I just don't know.
Because it seems like the company probably
But
now
Starlink
who
is-
has most of the satellites.
Starlink
in
isn't
the,
doing. It's not really GPS. It's more like it's data transmission.
Yeah, I
but
think-
for data transmission, exactly.
I think it's
you
mostly
need-
data transmission. Yeah. I think the most of the satellites use rubidium clocks because the reliability is best. The GPS system, I think, uses mostly rubidium clocks
Why rubidium?
because the reliability is better.
Oh, so why is the reliability better?
It's been engineered to death.
Engineering.
It's been engineered to death.
Is there any fundamental difference between rubidium? Is it the wavelengths or?
Well,
like-
the frequency is lower,
okay.
but I think, I mean, my understanding in the GPS problem is that the driving term is reliability.
Mm-hmm.
The satellite is up there and you can't repair it. It's going to be what it's going to be. So the driving term is reliability. But I'm not. That's not my business. But the rubidium standards have been engineered to death.
Since the atomic clocks, since they're so sensitive, are they used as sensors also?
Yes.
Like instead of blocking out all these noise sources, are they
There-
used as sensors
there,
for
there are
different signals?
there are for example, the frequency standards in general are used as the standard of voltage by an effect called the Josephson effect, in which relates frequency and voltage. So the standard of voltage is defined in terms of frequency. The standard of length is defined in terms of frequency. Namely, the 1 meter is the length at which light travels by 1 over the speed of light, essentially. That defines the meter. So the time interval of 1 meter is where light travels 1 over the speed of light. That's the definition of the meter. The definition of the volt is based on the Josephson effect. There are proposals to use relativity, the relativistic variation, to measure little g, to measure the acceleration of gravity, where when the Earth goes up and down, the gravitational potential changes, and you would see that as a relativistic effect on a change in the frequency. And so that is a proposal which has been around, and the problem with that proposal is a sensitivity issue. The effect is small, so you need a very stable clock in order to make it work.
I see. Yeah, I've been also thinking on the other side as like expanding from like GPS type of system towards when we move to the outer space. How do we do the communication? And
I don't know.
Distribution.
I don't know. I don't know. Okay, I think there's some discussion about a time on the moon. That is what the time. But there are relativistic problems because the moon, the gravitational potential on the moon is very different. So a clock on the moon, as observed from the Earth, would be running at a different frequency. That is, if you observed the clock on the moon and you observed it from the Earth, you would see the frequency is different because the gravitational potential of the clock and the gravitational potential of the receiver are different. So
Are there now clocks on the moon? Like
there
maybe
aren't
some rovers?
there aren't physical clocks on the moon, but there are discussions about what would the clock be if there were a physical clock on the moon. I think there have been some tests. Not so much. I don't think there are clocks on the moon, but I think there are clocks in orbit. I think there have been tests of clocks in orbit on the moon. I'm not an expert on that, but
it's like a satellite.
yeah, I think so. I think there were satellite, but again, I'm not sure I know the right answer for that.
Is it the same on the Mars?
No, Mars is different because Mars has a different gravitational potential. Also, there will be Doppler shifts because the distance between the Earth and Mars is changing as the orbits so the signals are very complicated. That is, looking at a clock on the moon from the Earth is a very difficult business. Because there are general relativistic effects because the gravitational potential is different, but there are also Doppler shifts. That is
The movement on the moon.
because you're observing on a moving platform from a moving platform.
I see.
So it's a very complicated business.
So maybe also, since we're trying to project like in the future, like let's say if you were given some unlimited resources or big resources, what kind of project would you spend them on?
See, I think the main problem. Let me come back to what I think the main problem is. The main problem is not the clocks; it's the distribution mechanism.
I see.
And now I think June and I would differ on that. Okay, he would, if you gave him a lot of money, he would build a better clock. But I would build a better distribution system.
How would you do that?
I don't know. Okay, because I don't. That's one of the problems. I don't know. I need to define a method. I mean, I'm not up to engineering yet. I'm still back at physics. Okay, I don't know. And I know how to make incremental improvements on what exists, but I don't know how to make a fundamental improvement. I don't know. And it's not, when I say I don't know, I mean the community doesn't know. There's no obvious method. There's no obvious next step. Okay. Whereas, in that sense, June and I would look at the problem differently. He would just build a better clock. There's nothing wrong with that. That's, we need each other. Okay. We need each other. Okay.
And coming back to UTC, is it also that kind of problem is solved? The world is happy at this point.
Well, but you see,
we need to move to like
no.
standards.
But you see the when you say the problem is solved at some level. For example, if you ask me what is the difference between the time in the United States and the time in Germany, suppose I asked you that. Suppose you would ask me that question. The answer is I would say it's a few nanoseconds. Okay, is that good enough? All right, and the answer is maybe that's good enough, or maybe that's not. Okay, so if an application were to appear, which would require more accuracy, greater accuracy, the problem is not solved.
So do this also maybe like the stock market people would.
Well, the stock market is crude by comparison. I mean, the stock market is at the millisecond or microsecond. I mean, it's not the same. At the same level of problem.
But do they compete for this? Who has faster?
Sure. But
information.
But there it's at least my perception.
It's more about latency.
Is that it's latency? It's channel delay that's the problem.
Yeah.
Who puts the order early, or what's the?
Stuff like that. Who gets the information of the price earlier? So
people
would
I
connect fibers directly to.
I
think next to.
I think the stock market is a channel delay. It's an information transfer issue.
Yeah, so it's speed of light problem. You need to speed up light.
Yeah,
but then they need the processing to do.
Yeah, that's
much faster.
Of course, that's another.
Well, so the answer is you want to have your system as close to the stock market as you can possibly stand it. All right, but that's a.
Or like a fiber with a higher refractive
index, but I think you put it right in the same building. I mean, you don't want a long fiber; you want a short fiber. So you have it in the same building, but I don't think that's a. That's not a.
That's not a clock question.
That's not a clock question.
But then would it make sense to have distributed stock exchange
to avoid this?
I think the answer with distributed stock exchange is a question of information transfer.
Yeah.
Okay. For example, if something happens so that the price of stock in New York goes up, but you only learn about it 30 milliseconds later, well, it may be too late. Okay.
But isn't it the same? Like, let's say options are traded, like, I don't know, in Chicago, a stock exchange, and then.
Well, but wait a minute, but it's 1,000 miles of Chicago.
Yeah.
So it's going to take whatever it is, a few milliseconds for the information to get to you.
I have a totally, unrelated, completely orthogonal question. So room's full of books, right? Your office full of books. A lot of these books are actually programming books.
Yeah.
So a lot of them are books like programming in Python 3,
C++.
That's right.
That's right.
What did you spend a lot of it seems like you're a programmer.
Yeah.
Why did you need to learn all these languages? I feel like there's 7 different
Oh,
languages here.
well, I think that well,
I feel like I'm in the room. You know, it's like you work for a tech company.
well,
you know.
well, but in some ways I do. Okay, I think the part of the answer is historical.
Okay.
Okay, when I started out, everything was done in assembly language. There were no higher level languages, so everything was done in machine language. Okay, so if you had come to my office 50 years ago, you would have seen books on machine language, on assembly language, and then the next step was Fortran. All right, and the next step in Fortran was C or C++ or whatever, and now it's Python. Right, so I keep learning new languages. I'm not sure what.
Now it is prompting.
What?
Prompting, making the prompts in the GPT.
Yeah, I mean, I used to make EPROMs. I used to burn EPROMs. Okay, but that was.
Now it's English. Now it's back to who made the law.
I understand, but that was. Now the latest thing, for example, outside I have FPGA devices.
I see.
Well, I have to learn FPGA programming. Well, that's not the same. It's a different language. It's
Verilog or like
it's Verilog.
VGL.
Yeah, it's like C, but it's not like C. It's different. Okay, and what can I say? You have to but you see, I never throw any of these books away, so I have all the ancient books. Okay, over there, those are the hardware books. Okay, that's the TTL books and the DTL books. But
so in this atomic, in the cesium clocks which you have in the other room, is it like the electronics and the feedback loop? Is it implemented on the like embedded controllers of PGA, or I don't know, people are doing like ASICs, like application specific?
I don't know
circuits?
Because it's a commercial device.
Okay.
My guess is it's an FPGA, but I don't really know. No, that device is pretty old. It was probably done with discrete electronics. It was before FPGAs. It was probably done with discrete electronics, and some kind of microprocessor. The great ancestor of a Raspberry Pi, but the great ancestor of it. Okay, I mean when I first started, we were using 8080s and 4040s, 404s, which were very dumb chips, PDP-8s. They were 8-bit chips, 12-bit chips, and they were single chip systems.
That's all from Intel, or
Sorry?
Intel chips, or what is Texas Instrument?
I think Texas Instruments. I don't remember. I maybe Intel. I just don't remember anymore. It's so long ago. It was 40. It may have been Intel. I just don't remember.
I see.
But it was all done in machine language. It was we had to burn it into an EEPROM. There was no compilers. You burned it into an EEPROM, and then you carried the EEPROM over to the. I mean, you had a development system, and you burned the EEPROM, and you carried the EEPROM over to the device, and burned, and so the device had no compiler, and you couldn't change the program. I mean, the FPGAs work the same way. You can't change the program in FPGA. You know, it is what it is. If you want to change it, you have to go back to the development system.
Do you have any advice for people getting into science, into physics? You know, young people today, based on your path through
learn as many different things as you can. Learn as many different things as you can. Okay. I think. Okay, when I started out, I had to know glass blowing. Okay, because the vacuum systems in those days were made out of glass. So I learned glass blowing. I learned machine shop.
Were you a good glass blower?
No, I was but I could make a system that would work.
Yeah.
But no, I was not a good glass blower. I was a chroming machinist. Okay, so I know how to machine things. I can machine things, but I'm not an instrument maker. I'm a chroming machinist. Okay, so I'm a chroming machinist. I'm a chroming glass blower. I can, you should learn everything. Okay, you should, especially as a student, because once you get a job, you're involved in the job and you don't have time to learn anymore. So you learn everything. Learn as much as you possibly can.
Okay, great.
Yeah, I don't know what else to say. All right.
That was fantastic.
Yeah, thank you.
Okay.
This was great.
All right.
We learned a lot.
That's true.
Sure.